IBESS, Climate Change and Energy Production Part 5, will introduce climate change with an initial look at climate and the natural cycles of temperature and change in the climate on Earth over long periods of time. Throughout this movie, carbon dioxide as a greenhouse gas will be mentioned, so I'll end the movie with a review of the greenhouse effect. Now, I covered the greenhouse effect thoroughly in Atmospheric Systems and Pollution Part 2. Review this movie as necessary. Understanding the greenhouse effect is critical to understanding climate change. The significant ideas are: climate change has been a normal feature of the Earth's history, but human activity has contributed to recent changes. There has been significant debate about the causes of climate change. Here is the outline of all the available movies in the Climate Change and Energy Production unit. Use this outline to find the movie you need for review. This movie is focused here. Let's get some important definitions out of the way. Take some notes. Climate is the state of the atmosphere prevailing in an area over a long period of time, whereas weather is the state of the atmosphere at a place and moment in time, short time period, with respect to heat, humidity, sunshine, and rain. The key distinction is time. Climate is a statistical long-term state of the atmosphere, while weather is what's happening in the atmosphere today. Remember that biomes reflect climate. A biome is a large community of plants and animals that occupies a distinct region defined by the climate and dominant vegetation. Weather is a state of the atmosphere at a place, at a moment in time, with respect to heat, humidity, sunshine, wind, and rain. Climate is the prevailing statistical atmospheric conditions of a region, such as temperature, humidity, precipitation, sunshine, cloudiness, winds, and these are averaged over a series of many, many years. In this map, you can see climate zones in the U.S. These zones are characterized by averages of light, rainfall, and temperature. These zones do not represent the weather in each zone today or tomorrow. Here is a relevant IB syllabus statement. Climate describes how the atmosphere behaves over relatively long periods of time, whereas weather describes the conditions in the atmosphere over a short period of time. Weather and climate are both affected by oceanic and atmospheric circulatory systems. Oceans absorb and move heat in the conveyor belt currents. The movement of heat around the Earth in wind and water influences climate and weather. Weather and climate are both affected by oceanic and atmospheric circulatory systems. Atmospheric circulation includes the tri-cellular model of airflow. The Hadley cell, the Ferrel cell, and the polar cell serve to move heat and are responsible for the location of specific biomes. I've covered this material before, so you should have some comfort with this detail. Air rises over the equator, forming clouds and rainfall over the equatorial regions. Air sinks 30 degrees north and south of the equator, resulting in dry conditions. The world's largest deserts occur approximately 30 degrees north and south of the equator. Air rises again at approximately 60 degrees north and south, resulting in rainfall, and air sinks over the poles, resulting in relatively low precipitation there. This is the tri-cellular model in review. The high detail was covered earlier in the course. Here are the relevant IB syllabus statements. Weather and climate are affected by oceanic and atmospheric circulatory systems. Explain the distribution of biomes based on global variation, precipitation, and temperature using the tri-cellular model of atmospheric circulation. Once again, on the tri-cellular model of atmospheric circulation, just to strengthen and review, air rises over the equator because of the high angle of solar radiation at the equator. Air cools at high altitude. Water vapor condenses at altitude, resulting in high rainfall over equatorial regions. Air sinks 30 degrees north and south of the equator. Sinking air warms as it approaches the Earth's surface. Water in the air evaporates, no condensing, thus no rain, dry conditions. Deserts 30 degrees north and south of the equator are the biggest in the world. This is the Hadley cell that I've just described. Air continues to cycle, rising at approximately 60 degrees north and south with the same effect as the rising air over the equator, clouds and rainfall. And air sinks over the poles with the same effect as air sinking at 30 degrees north or south of the equator, no clouds, and it's dry. Here's a nice image of the Hadley cell. I've described the movement of air and the changes in water in words on this slide. Stop the movie now. Take some notes if you have forgotten the tri-cellular model of atmospheric circulation. So that brings us to this IB syllabus statement. Climate change has been a normal feature of the Earth's history. Now, in the slides to come, I will describe cycles of temperature change throughout Earth's history, and I'll present some of the data. And I'll introduce some of the reasons for the climate change controversy. Here's a cartoon to keep things light, but remember that whenever rapid environmental change occurs, natural selection accelerates. Populations must adapt, evolve, and if the environmental change is rapid, some species may not make it. As I start in on the statement, climate change has been a normal feature of the Earth's history, I would encourage you not to take a lot of notes. Just take in the big picture concepts that climate has changed over time as part of natural cyclical events. Okay, here we go. The Earth has had variations in its temperature over time for a variety of reasons, and I would like to present those reasons here. First, there's variation in the Earth's position relative to the Sun. There are periodic changes in the Earth's orbit around the Sun. Some orbits are more elliptical than others, and you can imagine how a shift in the distance between the Sun and the Earth over time would influence temperature over time. Secondly, the Earth's tilt has not always been 23.5 degrees off the vertical axis as it is today. The angle of rotation rocks back and forth from 22.5 degrees to 24.5 degrees, and the tilt of the Earth affects the angle at which solar radiation strikes the Earth. This would affect regional temperatures across the globe. Lastly, the Earth wobbles in its rotation in a process called precession, and this also influences the angle of solar radiation regionally, thus changes in the Earth's temperature over time. These three processes that you can see on this slide cause variation in the Earth's temperatures, and they are cyclical over long spans of time. I'll show you more on this in the slides to come. Again, no notes, just take in the big picture concepts here. But I'd like to add one more idea. Sunspots, flares of energy from the sun. Solar flares or sunspots have also tended to be cyclical. There are times when sunspots are stronger and times when they are less strong. Sunspots also influence the Earth's average temperature. Here is a graph that shows time here along this x-axis back to 1 million years ago. And here are the three different cycles of the Earth's position relative to the Sun that I mentioned on the last slide. And sunspots are here. But we can focus on the bottom here to see that there were times when the Earth was warmer and times when the Earth was colder. And notice the cyclical nature of the change in the Earth's temperature. The interaction of these four factors influence the Earth's temperature at any one moment in time, and as these four factors cycle, so does the Earth's temperature over time. Now you may be asking, how do we know about temperature 1 million years ago? And that's a good question. I'll talk about how we know this later in this movie, but you can see the cyclical nature of the Earth's temperature over time, and that's the most important thing for you to take from this slide. Here are two graphs that show sunspot number. Remember, sunspots are solar flares. You can see how sunspots increase and decrease over time, and you can imagine how this might be responsible, partly responsible, for altering the Earth's temperature over time in a cyclical manner. So, as we think about climate change today, you should be asking yourself the question, are we recording warmer temperatures today relative to any time in the past? In other words, what's unique about a changing climate today relative to changes that have naturally occurred in the past? So how do we estimate the temperatures of the Earth before 1850, before a time when we had thermometers that we would deem as reliable instruments? Well, what we use is what's called proxy data, indirect data, and my use of the term indirect should be familiar to you because we have talked about direct and indirect measurements. So all of our estimates of temperature prior to 1850 would be indirect, also known as proxy data. To estimate past temperatures, the following indirect measurements are used. First, tree ring analysis. We have trees that will live between 3,000 to 6,000 years, and we can examine the rings within the trees to see the years that have been strong in growth and the years when growth has been poor, and then we can interpret that data to indirectly estimate temperature and possible carbon dioxide levels. Secondly, we have human records of crop harvests, good years and bad years, and we can interpret harvest data with respect to the Earth's temperature. Thirdly, we have ice cores that provide data stretching back 400,000 years plus, and we can measure levels of carbon dioxide in bubbles of air trapped in the ice, and from those levels of carbon dioxide, we can interpret temperature. And we can look at ratios of isotope 18 of oxygen and isotope 16 of oxygen. I won't go into the detail of the ratio, but this ratio gives us a hint as to the temperature of the Earth. And lastly, we can look at tree line data along mountain slopes. When the tree line goes upslope or downslope, we can interpret these changes with respect to the Earth's temperature. Now, before leaving this slide, let me remind you that in using proxy data, indirect data, there is greater uncertainty. The plus-minus error with indirect data is much larger than when using direct data. Evaluate, evaluate, evaluate. I'll be showing you some of all of this in the slides to come. Here's a slide to show you how we use tree ring analysis to indirectly estimate temperatures. You can see a wide ring right here indicating a year of good growth, warmer temperatures, and we have some rings here that are narrow indicating poor growth, either a cold year or a dry year. Again, we have trees that live from 3,000 to 6,000 years, and we can analyze the rings to interpret past temperatures. Here are images to show how ice cores are taken. A drill bores deep into the ice on Antarctica or in Greenland, and these cores are drawn from the ice and saved, preserved, kept frozen. The bubbles of air trapped in the ice are analyzed for the concentration of carbon dioxide. These cores run deep enough to go back 400,000 to 700,000 years. The relationship of temperature and carbon dioxide in the story of climate change is an intimate one. Pay close attention to this relationship as we move forward. But before looking at how we make sense of the collected data, let me put up this IB syllabus statement. Global climate models are complex, and there is a degree of uncertainty regarding the accuracy of their predictions. You should be having an aha moment here. Uncertainty with indirect data is large. And now you know something about why there has been significant debate about the causes of climate change. So here at the top is the list of indirect data sources. Remember, indirect data have greater uncertainty, but here's what gets done. Indirect data gets calibrated using data collected today on the Earth's temperature and carbon dioxide levels. For example, we would measure the width of a tree ring this year, and along with today's average temperature and carbon dioxide levels, calibrate the tree rings from older rings in older trees living thousands of years ago. So say, for example, if the ring was of X width today, and today's temperature and CO2 levels were recorded, then the 2,000-year-old ring with the same width would have been formed at the same temperature and carbon dioxide level. This might seem awkward, and it is, but this is how it gets done. As well, the indirect proxy data gets averaged. All the various data sources get put together into a single line, even though not all the units are the same. How do you average tree ring width with human records of crop harvest, with carbon dioxide levels out of bubbles in the ice, or ratios of oxygen 18 to oxygen 16? How do you average all of that? These data are not similar numbers. They don't have similar units, but people will put them together to make an estimate of past temperatures. And then, at the very end of the temperature curve, a curve generated from indirect data from the deep past to the present, we attach the modern thermometer-generated temperature record. So various scientists have attempted to reconstruct Northern Hemisphere temperatures over the last 1,000 years or so, and each of the curves represents a different reconstruction, and you can see how different the reconstructions are. But the question is, which one is most accurate? The most recent research is represented by the red line, and according to the red line, temperatures are rising as we approach the year 2000. Now, just a quick note, instrumental records are presented by the black line here, and you can see how the thermometer-generated data, the direct data, is simply attached at the end of the other curves. And you can see that the Earth's temperature appears to be increasing. Now, as you look at a graph like this, and you see this very high temperature here, and it appears to be alarming, keep in mind that the data presented here only goes back 1,000 years. So how do we know that this value is high relative to temperatures in the deep past? Now, this is a very interesting graph put out by the Intergovernmental Panel for Climate Change in 2001, and the data in blue, shown in blue, is the proxy data, the tree ring data, the coral ring data, ice cores, historical records. The black line is the average of all that proxy data. Smart statisticians average the various forms of indirect data to produce the black curve that you can see here, and this is our way of understanding past temperatures. Now, way out here to the right, we see the red curve. This is the instrumental data, the direct data using a thermometer, and it's attached at the end, and you can see how the temperature is rising. In gray is the standard deviation of the data, 2 standard deviations actually, to present the greater uncertainty in the proxy data. What you should notice is that the uncertainty is quite large. In fact, at any one time in the past, uncertainty tells us that the temperature might have been here or here, and we don't really know. And notice that some of these possible past temperatures are nearly as high as the directly measured temperatures of today. Thus, there is a lot of uncertainty in understanding the high temperature of today. As a last note, this graph is what is known as the hockey stick graph. This is the shaft of the stick, and this is the blade of the hockey stick, thus the name hockey stick graph. The IPCC also put out this graph showing the correlation between past temperatures and carbon dioxide concentrations in the atmosphere. What's interesting is that it shows CO2 increasing and then temperature increasing. Notice the temperature increases after the carbon dioxide increases, and there's a time lag. You can see the time lag here. Carbon dioxide increases first, and then temperatures follow. This would be the model of today. We're combusting fossil fuels, so carbon dioxide increases, and then temperatures increase. Now, while this graph does go back 160,000 years, what's interesting about it is that it conflicts with ice core data. In other words, is the change in temperature caused by changing carbon dioxide levels, as this graph suggests, or, as the ice core data suggests, changing temperatures cause a change in carbon dioxide levels? So again, this is part of the uncertainty, the controversy. What parameter forces the other? Does CO2 increase or force a temperature increase, or does an increase in temperature force a carbon dioxide increase? I would like to add my own editorial comment here. I think both scenarios are possible. Either parameter, temperature or carbon dioxide, could force the other, so that to lock yourself into assumptions embedded in one data set or the other would be limiting. In this graph, we have Antarctic ice core data that goes back 400,000 years, and the red curve is carbon dioxide data, and the blue curve is temperature data. Notice that the blue curve, temperature, rises first, with carbon dioxide following. Temperature first, CO2 follows. So ice core data suggests that temperature increase precedes carbon dioxide increase. But today, the cause and effect relationship for climate change is reversed. CO2 increases first and temperature follows. Again, this is part of the uncertainty, the controversy. Keep your mind open. Remain aware of the uncertainties in the discussion, including the use of indirect data versus direct data. It's possible that, historically, temperature increases did force carbon dioxide increase, but in today's world, that's not the way we see it. Anthropogenic climate change suggests that the combustion of fossil fuels releases carbon dioxide, and the carbon dioxide increase is forcing increases in global temperature, climate change. So here's a relevant IB syllabus statement. Climate change has been a normal feature of the Earth's history, but human activity has contributed to recent changes. Let's look at the recent changes. A graph like this can be used to convey various pieces of information, and it's important for you, whenever you read a graph, to be a discerning reader. Let's look at the x-axis carefully and notice that the graph does not go very far back in time. We can see carbon dioxide concentrations here on this y-axis and average surface temperature on this y-axis. Carbon dioxide concentrations are increasing, and that's not disputed. The data from monitoring stations in Hawaii and Australia are reliable and well regarded. Temperature fluctuates around the carbon dioxide level, and there appears to be a general increase in temperature. A proponent of anthropogenic climate change would say, look, the temperature is going up and it's following the increase in CO2, and this is what's being observed. As the CO2 is increasing, the temperature in turn also increases. Now, a climate skeptic would say, but this graph only goes back 40 to 50 years. So how do we really know that these temperatures, the temperatures out here to the right, are higher than they have been in the past? How do we really know that the increase in CO2 is because of human activities? We're not really sure that the temperature increase seen here means anything with respect to past temperatures of the Earth. And the ice core data suggests that temperature change would precede carbon dioxide change. This is a graph that shows the instrumental temperature change, direct data, over the last 150 years or so, data that has come from thermometers. Climate change proponents would argue that what's important about the data is not so much the high temperature at any one moment in time, but the rate of change as seen in the slope of the curve. Climate change proponents would argue that that's what's most important. It's the rate of change, that this much change over a relatively short period of time indicates anthropogenic climate change. So here's a definition of climate change. It's an increase in Earth's average temperature with more energy contained in air and water vapor. A change in global or regional climate patterns since the mid to late 20th century onwards. And it's caused by an enhanced greenhouse effect due to the increase in greenhouse gases, particularly carbon dioxide, in the atmosphere. Human activities, particularly the combustion of fossil fuels, are increasing atmospheric carbon dioxide levels. In other words, an increase in the greenhouse gases results in an enhanced greenhouse effect, where these gases are trapping the long wavelengths radiated from the surface of the Earth, acting like a blanket, causing an increase in the average temperature of the Earth. Let's review the greenhouse effect as we bring this movie to a close. Here are the relevant IB syllabus statements. Describe and explain the greenhouse effect. The greenhouse effect of the atmosphere is a natural and necessary phenomenon, maintaining suitable temperatures for living systems. The Earth's average temperature is 15 degrees C. The Earth is warm due to the greenhouse gases. Without the greenhouse gases, the Earth would be an inhospitable negative 15 degrees C. The greenhouse gases are important. They play an important role in keeping the Earth warm. 15 degrees C is an average temperature, but the graph shows that the Earth has variation in temperature due to the spherical nature of the Earth and the tilt of the Earth on its rotational axis. Different regions of the Earth receive different amounts of solar energy. Consider the average temperature at the equatorial latitude as compared to the average temperature of the polar latitudes. 15 degrees C is the Earth's average temperature, and climate change is an increase in the Earth's average temperature. The greenhouse effect is explained as follows. Short wavelength, visible wavelength, solar energy arrives at the surface of the Earth. Long wavelength, infrared energy is radiated back out toward the universe. Greenhouse gases absorb the long infrared wavelengths and re-radiate heat, infrared, back to the Earth, keeping the average temperature of the Earth 15 degrees C. Solar energy streams toward the Earth, and some of that energy is reflected, and some of the energy is removed by stratospheric ozone. UV wavelength is absorbed by stratospheric ozone, and some short wavelength energy does reach the surface of the Earth. And in turn, the Earth radiates long infrared wavelengths back out, and some of those long infrared wavelengths are radiated back to the Earth by the greenhouse gases of the atmosphere. The trapping of infrared wavelengths by the greenhouse gases serve to keep the Earth warm. This is the greenhouse effect. Here is a relevant IB syllabus statement. Greenhouse gases are those atmospheric gases that absorb infrared radiation, causing global temperatures to be higher than they would otherwise be. Okay, do you have it? Here it is again. Solar energy streams toward the Earth. Some is reflected, but the short visible wavelengths reach the Earth's surface. Long wavelengths, infrared wavelengths, are radiated back out. The long infrared wavelengths are absorbed by the greenhouse gases, and then that infrared heat is radiated back to the Earth, keeping the Earth warm, a hospitable 15 degrees C. This is the greenhouse effect. I have two more slides on the greenhouse effect. In this slide, there is an image of the greenhouse to help clarify the greenhouse effect. We can see short wavelengths passing through the glass. The atmosphere is the glass. The glass represents the atmosphere. Short wavelengths pass through. The wavelengths are absorbed by the surface of the Earth and re-radiated as long wavelengths, infrared, back out, which are absorbed by the glass, absorbed by the atmosphere, absorbed by the greenhouse gases. And those wavelengths, in turn, are radiated back to the surface of the Earth. This is the greenhouse effect, and it is what keeps the average temperature of the Earth, 15 degrees C, warm. The enhanced greenhouse effect is the increase of greenhouse gases to the atmosphere by human activities serving to increase the average temperature of the Earth. Most of the world's scientists think that human activities that are resulting in more greenhouse gases, are responsible for changing the climate. But some people think that any change in the Earth's average temperature in recent times is nothing more than part of a natural cyclical change that the Earth has experienced over millions and millions of years. Some people think that while there is more carbon dioxide in the atmosphere, human activities are not responsible for that increase. Some suggest that the magnitude of the Earth's systems is too immense for humans to have an impact. But the consensus among scientists today is that human activities are causing a change in the Earth's average temperature. Anthropogenic climate change is happening. There are varying value systems on the subject of climate change. Some people with a Western capitalist value system or a technocentric value system might suggest that we should continue to drill for oil and continue to burn fossil fuels. Ecocentrists might focus on the plight of certain species as the climate changes, arguing that people must find alternative energy sources. Many people are invested financially in the fossil fuel industry. These people wield political clout with money and alternative facts. Some people follow political values without thinking for themselves. And as the world warms, are we taking notice of the increase? Can we discern the difference between weather and climate? Too often, a cold day in the summer leads people to suggest that the Earth's average temperature is not increasing. Too often, we latch on to 2 or 3 observations to support previously held beliefs. We need to be listening to our scientific community, a group of people doing their best to understand changes at the scale of the Earth. And feedback effects are difficult to predict, leaving room for political values to insert themselves. But shouldn't we be cautious before foolishly continuing with the status quo? And thus we have the precautionary principle: when extensive scientific knowledge on an issue is uncertain, actions should be cautious to ensure minimal harm. Better safe than sorry. And these are the IB syllabus statements to end the movie. There has been significant debate about the causes of climate change. There has been significant debate due to conflicting environmental value systems. And can you evaluate the contrasting views on the issue of climate change? And that brings us to the end of IB ESS Climate Change and Energy Production, Part 5.